again here. We are going to continue in the last chapter, that is called keto-enol tautomerism. Last time we have discussed what is a tautomerism and we cited the example of the keto-enol tautomerism. Keto-enol tautomerism, this time we are going to explain 11 of the things about the keto-enol tautomerism and intricacy of the keto-enol tautomerism. In case of tautomerism, there are two forms. One is keto form and another is enol form in case of keto-enol tautomerism. And both are in equilibrium. At equilibrium, both have a different concentration. The concentration of enol form at equilibrium is called enol content. This is called enol content. The enol content or enol form percentage at equilibrium is called enol content. Now, there are so many factors responsible for the stability of the keto or enol form of the tautomerism or enol content of the tautomerism. That is, one factor is nature of solvent, another factor is temperature, and most important factor itself is the stability of the molecule or the presence of acidic hydrogen or active methylene group. One example is here. See this very molecule. Here in this case, the methylene group is highly active and this hydrogen is highly acidic in nature. That's why this type of molecule always exists in enol form around 98%. As the activity of methylene group decreases, the enol count decreases there. Means as the acidic nature of hydrogen decreases, enol content is going to decrease there. Take the example of acetone. It is a keto form and enol form could be here like this, but the enol content will be only 0.01% here. So the activity or active methylene group makes enol count greater there. Another factor that is responsible for the stability of keto-enol tautomerism is the intramolecular hydrogen bonding. For example, in this case, molecule is going to make H bonding, intramolecular hydrogen bonding, and that's why it is a 6-member ring, and 6-member ring is highly stable. That's why its enol count is very high, around 80% and more enol count is there. 80%, yeah, 80 to 80% or more than that one. Another example is here, the steric effect. The steric effect is also very important to determine the stability of keto form or enol form. Take an example here. Here in this case, there are two bulky groups are present at alpha carbon, which makes molecule highly strained. And since this carbon is in sp3 hybridization, bond angle is 109 degree. That's why it is highly steric in nature, and steric hindrance effect or steric strain is very predominant there. But when it gets turned into enol form, enol form, this bond angle has increased up to 120 degree rather than 109 degree. That's why this makes molecule less steric strain, and that's why molecule is more stable. So enol count will be here greater in this very case rather than keto form, and makes molecule more stable. So there are another one is conjugate system. If there is a conjugate system happens, enol form is considered to be more stable than keto form. I'll take an example here. It is keto form, but if it get tautomerized into enol form, the conjugate system appears here. So due to the presence of conjugate system, enol form is said to be more stable than keto form. So there are so many factors responsible for the increase in enol content and so on. Thank you.